in this upcoming lecture series, I'm going to discuss some basic aspects of relativistic quantum mechanics. I'll first start with the relativistic wave equations. So the wave equation we have used so far in our undergraduate course doesn't satisfy the requirement of special theory of relativity, because these equations were developed in non-relativistic reason, and the Hamiltonian was non-relativistic. But also, these wave equations we have used in various physical problems like potential wells, potential states, etc., is of first order in time and second order in space coordinates, right? And this contradicts the space-time symmetry requirement of relativity. So there are two ways to get rid of these difficulties while using these wave equations in relativistic reason. So the first one is what we can do. We can use a relativistic Hamiltonian. We shall use a relativistic Hamiltonian for a free particle in place of non-relativistic one. Or alternately, we can develop a first order equation, obvious given equation in both space and time. So these are the two ways by which we can use these or transfer these non-relativistic equations into relativistic case. However, Schrodinger proposed the first case where he proposed the use of the development of a relativistic Hamiltonian for different system. And this type of equations was further detailed by Klein and Gordon, and those are popularly known as Klein-Gordon equations. But in this first approach, it was silent about the spin of the particle. So it is conventionally used to describe for spin zero particles like K meson, pi meson, etc. However, Dirac used this second idea. He developed his relativistic equation, which was first order in space and time. And it was also applicable for spin-half systems. So that is what is called Dirac equations. So in the upcoming lectures, I'll discuss about all these issues. So let us first discuss with this first approach, which is proposed by Schrodinger. So we shall develop a relativistic Hamiltonian. So in the non-relativistic equation, we have the Hamiltonian H, which was p square over 2m plus this b, which is the potential. So, and this p, what we use, this p was minus I h cross del, right? And energy E was I h cross del by del t. So these are the energy and momentum operators in classical physics for a free particle. And now we shall use these in relativistic case. So we know the relativistic energy momentum relations as E square equal to E square c square plus m square c to the power 4. Here m represents the rest mass of the particle. Just remember, instead of m0, we are writing m as the rest mass of the particle. Okay. Now we shall use the corresponding energy and momentum operator in this equation. So if we use that, what is this E? For in this case, if we use E equal to this I h cross del by del t square equal to c square into p square, that is minus I h cross del square plus m square c to the power 4. Right? So if we do this, it becomes minus h cross square del 2 del t2 equal to minus c square h cross square del square plus m square c to the power 4. Right? Okay. So now let us allow this operator, this equation 2, to operate on the wave function psi. Here psi is obviously a function of position and time. Okay, so let us operate this. So this is minus h cross square del 2 psi del t2 equal to minus h cross square c square into del square psi plus m square c to the power 4 into psi. Okay, so this takes the relativistic form. And this equation is Schrodinger's relativistic equation, or which is generally called the Klein-Gordon equation. Klein-Gordon equation. Okay, or let us write it in a different way. So if we take this del square operator in left hand side and divide with this c square h cross square, and after some mathematical rearrangement, what we shall get? We shall get this del square minus 1 upon c square del 2 del t2 of psi. Obviously, this is a function of r and t, is equal to m square c square over h cross square to psi. So in the next discussion, we shall write only psi instead of psi rt, and unless until specified. So this operator, this del square minus 1 upon c square by del square, we usually termed it as the D'Alembertian operator, or we write it at box square. So this box square psi t is equal to m square c square over h cross square into psi r. Okay. So this is the commonly known the Klein-Gordon equation in terms of the D'Alembertian operator form. So now let us go for a plane wave solution for it. So the plane wave is can be represented as say psi rt is equal to say e to the power I k dot r into e to the power minus I omega t. Right? So let us number this continuum. So this is 5. This is equation number 6. So this plane wave is an eigenfunction for both the energy and momentum operator. So the energy operator which has eigenvalue h cross omega, and the momentum operator has eigenvalue h cross k. So if we use these equations, this solution into this equation 5, what it yields? It yields this h cross omega square equal to c square into h cross k square plus m square c to the power 4. Or from here we can write this h cross omega is equal to plus minus under root c square h cross square k square plus m square c to the power 4. Okay. So we got an important issues here. So what these equations suggest? These equations suggest that this energy eigenvalue h cross omega can take both positive and negative values. So Klein-Gordon equation was not able to give any consistent explanation for this negative energy. So now let us interpret the Klein-Gordon equation. So it will be discussed in the next lecture.